I'm going to redo this for one more time just to be sure. So ETS stands for Enhanced Transmission Selection. Basically, for data centers, you have multiple classes. Now we are using the word classes, not priorities. That is one important difference, because previously the word priority was much more strict. That meant you couldn't really transmit priority 6 if there is so many priority 7 traffic. Now this is all gone. Now we have classes. And the classes are grouped because you don't want to manage 8 different policies, so you have 2 or 3 policies. So first policy group consists of these, second policy group is this, and third policy group, and you could have 4, 5, 6, as many as you want. You could have 8 groups. For each group you have some reservation, maybe not be for each group, for some of the groups you have some reservations. So here in this example we have 3 groups, and for group 3 we have reservation of 3, and for group 2 we have reservation of 5. And let's assume these are all in just to be a little bit closer to the reality, is in gigabits. 3 gigabits and 5 gigabit, total link is 10 gigabit. Alright, so if this is the traffic sent and this is the traffic transmitted, the sent traffic in the first time interval, group 3 sent 2, group 2 sent 2, and group 1 sent 1. The link is underloaded, there is no question. Everybody gets whatever they want. So everybody gets 2, 2, 1 on this side. In the second time interval, they sent 3, 5, and 3. This is guaranteed 3, nothing is left over. This is guaranteed 5, nothing is left over. This is basically 3 and 5 is 8, so only 2 can get through. This is not guaranteed anything, but 2 will get through. So this is the allocation. In the third part, we have total demand of 12. This one demands 4, this one demands 6, and this one demands 2. So this one gets 3 because that is guaranteed. This one gets 5, that is guaranteed. They get 2. And then they don't get any more than whatever they had reserved. If this 2 would not be there, if there was no traffic here, then maybe they will get. Okay? So while we want to give the best effort, this is actually the best effort traffic, some minimum, because we don't want to make it 0 because all the connections will break. Even if they're best effort, they will break. TCP connections will break. So we give them 2, and then and since the link is overloaded, nobody else got more than what they reserved. If the link was underloaded, then they could get more than what they reserved. Let's say if nobody asked for anything, this guy asked for 9, they will get 9.
So I have
Yeah.
some quick questions. Is that actually, so the time 3, I mean the time is 3. So the 4 is that shorter than the left one because the value is 4, but I'm not sure why it's shorter than the other
3, 7 and 3. That's a drawing error.
Okay. I was confused.
I did not draw it correctly. I mean, I drew it all this and then I forgot probably to make it 4.
Okay, so number 4 is right?
Yeah, number is right.
Yeah, number is right.
Can you take a hand out and mark that and give it to me?
You might have mentioned already, but could you explain one more time what's the difference between PFC and strict priority?
Okay. PFC stands for Priority Based Flow Control. Strict priority comes from the old days. Original Ethernet had strict priority. Not original Ethernet. Original Ethernet had nothing. But when we came to 802.1q, which is the VLAN, in the VLAN we put 3 bits for priority. Those were strict at that time. And so a lot of priorities got starved. You know what that means, right? The lowest priority got starved and they really couldn't use the network that much because somebody else will come in and they would be last in the queue. And so that was not a good idea. Strict priority was not a good idea. So now they have come to what we call classes. Classes have no connotation of being higher or lower. Like you have a black class and white class. We don't say that one class is higher than the other class. See what I mean? So priorities are different than the classes. Classes have no higher and lower understanding, right? So now we have 8 classes. But since they are called priorities, so the thing is, PFC was priority based flow control. What that did was the pause, which was for all priorities. Previously, pause was just, when the pause was introduced, pause was probably not there in the original Ethernet either. So whenever the pause was introduced, they said everything will stop. And that broke everything. Right? They think that was not a good idea. They said we can stop something, but not everything. So now that is what priority based flow control is. You could start one priority 5. Okay? Everybody understand that? How the Ethernet is changing? Alright. So the last thing they added is quantized congestion notification, QCN. And believe it or not, we worked very hard to get our scheme in. We fought with QCN. The story about QCN is we had done some original work on something called ECN, explicit congestion notification, which is now part of the IP standards and it is used in the IP. Somebody called me from IEEE and said, why don't we apply that to Ethernet? And I went there and said, no, this is too old. We did that work in 1986, and now, with high-speed networks, you really need, better scheme, this and that. So we did, quite a bit of work, but we lost. And some other professor took that bit stuff and finally made this scheme. They sort of won in the sense that political battle, this is a standard, but it is not being implemented, as you will see in a minute. So this is somewhat close to my heart thing, we spent 2 years on this. This is QA2 2010 standard, dynamic congestion notification. And the way it works is that a switch, whenever its queues become big, it sends a source quench message to the source. What is source quench? Source quench message is not pause, but it tells the switch that please stop. I am in trouble. Okay, so it just notices whichever packet happens to be coming in. Hopefully it is random, and says, look, the queue is too big. You are coming in at the wrong time. Please reduce yourself. And there is some probability associated there too. You just don't tell people coming in at the end that you are wrong. Maybe people who came in the front were wrong. So there is some probability with them. You admit them, or with some probability you reject them, or not reject them. Basically, you send a source quench. Source quench goes all the way to the source. It doesn't stop at the intermediate switches. It goes all the way to the source. And then the source stops. Source stops means reduces its load. And then some time later it increases its load. Alright? So in the source quench, some first few bytes of the packet are sent. So the source can figure out which flow is it that is causing problem. Because source might be sending packets to 1,000 places. Not all of them are going to the congested area. But some went to the congested area, so it knows that, packets going to Germany are congested. So it will just stop those flows. Alright? So now that is the scheme. Everybody understand this scheme? Very simple. If your queues are long, you just send a source quench to the packets that are coming in, to the sources, and say please reduce, and the sources reduce. Alright? And the reason they had to put this in Ethernet is because something else that we are going to talk about later, fiber channel has this. Not source quench. They have a flow control, just like TCP IP, where not a single packet is lost. And people were not happy with Ethernet because packets were lost. So they said we want to make sure that Ethernet doesn't lose the packet, and therefore we want to put this standard. And so this scheme was selected for that reason. So this was selected. In our scheme, it was the opposite of this. Basically, in our scheme, what happened was that the switches would keep some kind of averaging on the queues. So you cannot just use the queues as they are. You really have to keep averaging. And then you send some signal to the sources, and the sources will reduce, and then when you want to increase, you send them increased signal. So that was a slightly different feedback, but it was different, right? So the reason our scheme lasts is because the standards are dominated by the switch people. These host people don't come to the standards for whatever reason. All hosts are made by Intel, probably one company. So they come to the standards actually, but switches are hundreds of companies making switches. I was told, look, we don't want to do anything complex. And we have 50 ports. And 50 ports means, we are not going to do 50 queues, averaging this and that. So this is too complex. So this one basically what it did was it put the complexity to the source. The source is very complex. The switch is very simple. Now source has to remember that I sent a packet to Germany a second ago, and that flow has to be done. So it has to keep per flow state. And it has to reduce that flow and not everything else, right? So the story now is that it is implemented in all the switches, but it is not implemented in any host. All right? The end result is you don't get any congestion control. However, marketing people are very happy because they can market and kill fiber channel, which they did. Basically that, we have the same feature that you have. All right, but in the real world, it was, and I was told that, look, we really don't really want to do anything. We just want to have a stamp that we have congestion control. And it doesn't matter. All right, QCN. With that, I think I finished everything on QCN. Yeah, there's another problem with this scheme too, is that source may not be real source. Source may be a router, which is forwarding from some other Ethernet, right? And so if you tell them to slow down, what are they going to do? They cannot slow down. They will just throw the packet which are coming in from this real source. They can slow down, but that will fill up the queues, right? So the only way congestion control works is when the real source stops. Because the real source can stop because it is keeping the packets on the disk and reading from the disk, it is reading some files and all that. So it can stop, but the routers cannot. Anything in between cannot. So that's another reason is that it does not really help. But anyway, it is done, final, and we are on business. And the professor who won actually made a few $100 million because he worked for a Cisco company. But having said all that, now the next thing they did was the DCBX. DCBX is Data Center Bridging Exchange. It's a great name for LLDP extension. If you remember LLDP, does anybody remember what is LLDP? All right. Now I got to give homework for reading maybe. Is that I give you some reading and then I ask the quiz right up front in the class at the beginning, and this is what I will do from next class onwards. Because we covered LLDP in the last class. In this class, nobody knows it. And so nobody really bothered except that particular homework which was spanning tree. You read of spanning tree, but you did not read LLDP because that was not in the homework. Right? So from now on, the class beginning would be with a quiz. And we will collect those quizzes. So we will know how much people have read. Alright, is that acceptable? Good for you guys, right? I mean, otherwise you won't be following everything here.
Is it free for we gonna learn, or we have learned previously?
No, whatever you have learned. See, the thing is, I mean, if you didn't read DCBX, I wouldn't feel bad. But if you didn't learn you forgot totally about LLDP, then I'm in trouble because, I prepared the lecture so that we go step by step. Right? LLDP is Link Layer Discovery Protocol. Now, anybody remembers what does that do? Nobody remembers? Link Layer Discovery Protocol? Okay, that's not very good. Yeah.
I'm going to go and learn profile. I think it sends out messages and discovers either MAC addresses or hosts in the broadcast or one in the domain. I can't remember.
Yeah. So basically, it's very close to what you said, is that it's the neighbor discovery. So you find out what the neighbor knows, what language they speak, what features they support. So they just figure out what features they speak so that we can speak the same features. That is LLDP. There is a very similar protocol which is called shortest path bridging, in which we send out messages to the whole world to figure out what is the shortest path. That is different. But LLDP is simply neighbor discovery. It's not the network path, right? You just want to find out whether you support 100 gigabit, 10 gigabit, full duplex, whatever, frame size. So finding that out is LLDP. So LLDP now is, you remember, LLDP is very straightforward protocol. It is extendable in the sense that they just say that you send out TLV. What is TLV? What is TLV? Anybody? Yeah. Yeah, type, length and value. So you send out type, length and value, and you can have as many as you want. So you could have 15 type, length and values. But the types have to be standardized, because if you say I have type 15, so everybody has to know what type 15 means. So every time a new standard comes up, they describe what the new extensions are. So because we have this data center bridging, they have to specify the new TLVs. The new TLVs are priority group definition, what is the group bandwidth allocation, whether PFC is done or not, QCN is done or not, and things like that. So all these new features, whether the next guy supports or not, you have to find out. And that standard is called DCBX. Is that clear? If it is not clear, you should ask question right away so that it's clear. Yeah.
So what is actually the primary goal of DCBX?
Primary goal of DCBX so that we can implement what we call data center bridging, DCB, correctly. Otherwise, you wouldn't know whether I wouldn't know whether my neighbor supports QCN or not, or whether the source supports QCN or not, right? And here's the thing. Suppose you want to do that previous thing we did, the priority allocation. If I don't know that this group gets 2 megabit, and then I may not send it that way to you, right? So we have to negotiate all that. So that is what it is. We negotiate the capabilities. And the word negotiation is used here rather than information, is that if somebody says I want to give 3 megabits for something, you could say no, I want to give only 2 megabits, and then that will be settled by whatever rules have been set, right? So that kind of negotiation is possible automatically for the machines to do. All right, these are the new TLVs that are specified in this standard. Any question about that? Is it clear what I'm talking about? I don't see any head shaking either there, so probably it is not clear, but that brings us to the end of this lecture. Ethernet's use of IDs as addresses makes it very easy to move systems in the data center. That is the key point you learned. First is that the Ethernet addresses are IDs, and what addresses are locators? IP addresses are locators. So they are bad because every time you move, your address changes. Here your address remains the same, and that's very good. And so basically because of that, people don't want to go to IP layer, they just want to move VMs in the Ethernet layer. So the whole data center is one big Ethernet. Well, not really. You might have subnets, but you just move in one. Let me restate. So the whole data center may not be one big Ethernet. You generally move in one big Ethernet. You might have many big Ethernets in the data center, but you won't get out of the Ethernet into another, because that is a lot more work. Okay? Second message is that spanning tree, which was used to make it simple and stupid, is now really smart. Instead of that, we use a smart scheme, and those are the several smart things were done. First was rapid spanning tree, then multiple spanning tree, and then shortest path bridging. Shortest path bridging is just putting OSPF in layer 2. Slowly we start wondering why do we need IP in the first place? Because everything Ethernet is going to do. And the second thing is, what is Ethernet? Actually, the whole Ethernet previously was defined by CSMA-CD. There is no CSMA-CD anymore. So what is Ethernet? Ethernet is a frame format. As long as you send packets in this frame format, it is Ethernet, period. Ethernet is signaling. Ethernet is control plane, but not access anymore. Access is very straightforward. Everybody is line to line, point to point. So everybody speaks all the time. VLANs, virtual LANs, they allow different non-trusting entities to share an Ethernet network. With VLANs, we can put many different departments of the same company into the same VLAN and and not have to worry about it because they will not see each other's broadcast. And then the data center bridging extensions, there are 4 of them, 4 or 5, I forget. But basically, let's go one by one. One was priority based flow control. There was enhanced transmission selection. Priority based flow control simply said that you send pause and that stops only one priority. Enhanced transmission selection said that you can reserve bandwidth. QCN was another one. QCN simply did the congestion control. And the final thing was DCBX, which was extension to LLDP, so that we can exchange our capability. All right? Clear? Any question about anything? Okay. So as before, I really want to make sure that by next class when you come on bench day, you have read all these Wikipedia things. And I will ask questions just to make sure that.
So actually I have questions.
Yeah. Yeah.
About the internet. So actually the task group, Jim was the book. Actually the CSMA and CD is the main it was for internet, right?
Yeah.
So what else are we using for in internet? So
Nothing.
nothing.
I mean, if you want to call this nothing, basically when you have point-to-point links, so what happens is basically we have 8 copper wires going, right? 4 on 4 I send to him, and on 4 he sends to me all the time.
Yeah.
There is no access required.
So any detection,
There is no collision, there is no detection. The thing is, what you do have to detect is that when I'm sending, I'm framing it so that basically I send zeros all the time, and that means nothing. And when I start sending something, I send something different first in the beginning to make sure that a new frame is coming. And then they start looking for the source address, destination address, all that. That is all Ethernet. Ethernet is framing.
Yeah, but we share the same Cooper, right?
So there are 8 copper wires,
Yeah.
4 going this way, 4 going this way.
Was it because it's a full duplex? Is it
Full duplex, yeah.
because of full duplex?
Yeah. Everything is full duplex today.
Switch, right? Switch. Usually go to shared link.
Yeah.
Switch network.
Everything is point to point now.
Right now, even in this is a building like this.
Even in your home. Everybody understands why it is switched in your home? Does anybody have a hub in their home? Nobody has a hub. When you go to buy anything is called switch. Hubs they don't sell anymore. In my days I bought a hub, but those are long gone. Yeah.
I just had a quick question. You mentioned with the ETS, it guarantees a certain amount of bandwidth, so a certain amount of patents are given out for a particular user. Does QCN break the ETS?
So actually, that question is kind of a mute question. Whether if you got a 3 megabit guarantee, would you get a QCN? I suppose not, because I will know that you are part of this, and so that queue will, as long as you send only 3, you would not get a QCN. But if you suppose send 4, then you might get a QCN. Yeah.
So the second one, the sending tree is not efficient, right? Regarding the resource. And everybody uses the end-to-end short pass. Is there any pattern alternative for this?
Better
Routing
what?
path, for example, okay, for the wireless network, if all the routing paths take the shortest one, there may be some overlapping in the bottleneck node.
Yeah, okay, all right. So the question is, spanning tree did cause a bottleneck because everything went through the root, or much of the traffic went through the root. Much of the traffic, not everything. Right? If you want to go from here to there, you have to go through the, whatever point joining point is, which generally was the root for many things. So there was a bottleneck. With shortest path, remember we also said that we also have called ECMP, which is equal cost multipath. If there are two paths from source to the destination, you take 50% this one and 50% that one. So really, that is the best you do. So nobody takes anything longer than the shortest, but there could be multiple shortest path, which is very common in the data center. If you notice in the data center, the way we do it, everybody has 2 and 2 and 2 and 2. They're all equal cost. Right? So there are lots of equal cost paths. And so everything gets used much better.
So kind of we have a load balancing, right?
Yeah, because of ECMP.
Okay. Thank you.
All right, with that we finish this lecture and move on.